So let's look at the calculus 2 exam 3 solutions with some detailed information and some explanations why and why not we use a certain technique. So the first question was this one. So it's asking you to find the arc length function. So it's not the arc length, but the arc length function. So arc length function. And then also it's giving a starting point, so the starting point is given. So that's the starting point. So normally, so what it looks like. So let's say, so you have a curve that can start at a point. So in this case, it is 0, 2/3. You can see that you get 2/3 if you plug in the value. So that's the starting point. And then, so this is the curve. So it's some kind of curve. So I'm just put a random curve. So they're asking to find the length function. So that means you're gonna pick a x value. So you're gonna calculate the length up to that x value. So what does matter is what is the starting x value and what is the ending x value. So we're gonna call let's say this is xx. So we're gonna find what is this length. Okay. So and we know the formula. So the formula is so we write it sx. That's the arc length. So it's going to be starting with a, that's the x coordinate, in this case 0 to x value, and then we have the function which is 1 plus, you take the derivative of the function and you're gonna square it and take the square root. So be careful, we are not gonna see that this is a function of x. We don't use x here, we use some other parameter. So let's say t. So that's important difference. So we don't use the exact same variable. Okay, so we use two different variables. If this is x, we use something else here. So it's like a t in this case. Okay, now it's very clear. So now what you want to do is to find the derivative. So let's start with the function. So it's clear what we do is, so let's start with the function. So we have fx equal to third and then 1 plus x squared 3 halves. So if you take the derivative, you're going to get f prime x by the chain rule. So we have 2/3 and then we have 3 halves and then 1 plus x squared 1 half times the derivative of the inside function, in this case 2x. So there are some simplifications, these two get cancelled out. So you get 2x times 1 plus x squared square root. So that's what we have. Now what we normally do is we're going to calculate 1 plus f prime t. So let's change the variable and write it. So we have 1 plus f prime t squared. So you have to square this. So but what's going to happen when you square this, and you can see that so we have 1 plus, you have to change the variable x to t. So we have and also we have to square it. So yeah, so let's try it. So we have 2t, which is the variable, and then 1 plus t squared square root, but you have to square the whole thing. So when you square the whole thing, what you get is 1 plus, when you square you get 4t, 4t squared, and we have 1 plus t squared, and you can see that this is simply 1 plus 4t squared plus 4t to the fourth power. Now this is the important thing. You always look for this kind of simplification for this kind of problems, otherwise it's a calculation going to be very difficult. So what we do, you can notice that um, if you look at the middle the term, what's the middle term? Middle term is, you can see the last term is the square of 2t squared. So right, if you look at the last term, the square of 2t squared. Middle term is the um, twice the twice 1 times 2t squared. So that means this is simply going to be a square. So that's what we notice. So you notice that this is simply going to be 1 plus take the square root of the last term, that is 2t squared, whole thing is squared. Just notice that. So that is the important observation. Why we want to do that? Because then once you take the square root, that simplifies very well. Okay, so that is the major observation here. So you always look for whether you can do that. It's not always the case, but sometimes you can do it like that. Good. Now because of that, we can simplify the function very easily. So let's look at that part now. That means your solution is going to be Sx, which is 0 to x. 0 is starting x coordinate. And then you can see here what we have is square root 1 plus 2t squared square root dt. Now what we notice, since this function is positive, you know that when you have we know this result, when you square and take the square root, it is not just x is absolute value of x, but since this function is positive, you can ignore the absolute, because this can happen simply x if x is greater than or equal to 0. So we can use that fact, and because of that you're going to get 0 to x 1 plus 2t squared dt. This is very easy to integrate. So if you integrate, you're going to get t plus 2/3 t cube, and then you can evaluate this at x and 0. When you plug in 0 is gone, so when you plug in x, you're going to get x plus 2/3 x cube. So yeah, so that's the answer for the arc length function. So if you look at the second part, what they're asking, find the length. Now they're asking the length. So asking the length for the range going from 0 to 1. So that means what we have is, so you have this curve. The x value ranges from 0 to 1. So that means since we have the arc length function which is valid for Sx, what we are simply doing is you calculate the value at x equal 1. Okay, so you're gonna set x equal 1 in the previous one, so that we are looking for simply S1. So S1 is 1 plus you can see 2/3 1 cube, that's 1. So if you take the common denominator, so this can be 5/3. Okay, that's a 5/3 whatever the unit uh, of the length. Okay, good. So let's go to the next problem. So in this problem they're asking, so the graph of uh, fx equal to square root x on the interval 1 to 3 revolve about the x-axis. That's very important. About what x-axis? What is the area of the surface generated? So asking us area of the surface generated. So if you kind of look at the region that we get is, so this is what the situation looks like. You really don't need this information, but I'm just doing it for clarification. So you have this curve, this is square root x, and then you can rotate about the x-axis. So it's going to jump to the other side. So it's going to create a surface, right? It's going to create a surface. So it's going from, so not the whole interval. So you're asking only the interval going from 1 to 3. Okay, 1 to 3. So that means we only worry about the surface in between these two numbers, these two x values. So that means it's going to go from here and then go from there, and then you can see that there's a small part between these two values. So that's the part we are looking for. What is this area of this part? That's the one. Okay, good. And then we know the function, so this is fx, and then So we have the formula. So what is the formula? So we know that the surface area formula, so which is we just say S for the surface. So what we have is it is A to B, and then we have 2 pi. Uh, so in this case, we have a y. So the y coordinate. So I'm going to mark the y coordinate. Uh, so it's a y coordinate, and then we have 1 plus. We normally write this one as dy by dx squared. It's the same thing. You can say prime square root. So that's the exact same term in the previous one, and dx. So that's the kind of formula that we have here. And you notice that this is a y because we rotate about the x-axis. That's why we have a y term there. Good. So as before, we just need the dy by dx term here. So let's calculate that and then plug in here. Okay. So let's see all the work now. So we're going to start with the function. So we have fx um, equal to square root x. So that means x1 half. So if you take the derivative f prime x or dy by dx, which is 2 1 half x to the negative 1 half. So if you simplify, you get 1 over square root x. These two we cancel. So now what we can do is we can calculate the term under the square root. So it's a 1 plus dy by dx squared. So which is 1 plus 1 over square root x squared. So you can see that this is 1 plus 1 over x. You can skip these most of the steps. You don't really need. I'm just showing all the steps. Now take the common denominator, which is x. So that means you multiply the first term by x top and bottom. So so what you get is x over x plus 1 over x. Again, these are all not necessary. Okay, I'm just showing for clarity. Okay, good. So that's what you get. Now what we're gonna do is we're gonna plug in that here into the formula. So let's plug in that into the formula. So that means S is in this case A is 1, B is 3, 2 pi, and then we have Y. Y means you can see it is 2 square root x, and then we only calculate 1 plus that, so that means it is x plus 1 over x square root dx. And then how to simplify this one? I'm going to take 4 pi out. So let's take 4 pi out of the integral. So 1, 2, 3. And then we have square root x. And then what's going to happen? The other one you can write as x plus 1 square root over square root dx. So you can see this get cancelled. Okay. So and then so what you get is this. So you have we have sx equal 4 pi, fx equal 4 pi 1 to 3 x plus 1 square root dx. Now you may feel like you want to use the u substitution. There's nothing wrong with that, but you really don't need that. So if you just say u equal x plus 1, you can see du equal dx. So if du equal dx situation, you can simply treat the x plus 1 terms just as x, because that's exactly what's going to happen here. So you can see that this simply equals to, by the 4 formula trick, remember the 4 formula trick that we discussed? From that, you can simply, because the derivative is simply 1 in this case, so you can simply create x plus 1 is just as x. So if you do that, you're going to get 4 pi. So you can see this is x plus 1 to the 1 half power, so you're going to add 1, so that's going to be 2/3 x plus 1 3 halves, evaluated at 3 and 1. So this is very clear, but if you use a u substitution, you will simply end up with that. So you really don't need that. You have shortcuts now. So we have 4 pi. So let's plug in the values first. So and then also you can see actually it would be better to take the 2/3 out. So that means it's going to be 8 pi over 3, and then what we're gonna do is we're gonna plug in the value here. So we plug in 3, it's gonna be 4 R3 halves, minus we plug in 1, which is 2 3 halves. Um, so how to simplify this? You can simplify this a little bit better, a little bit more. You can see this is simply first you take the square root, multiply the square root, it is 2, and then when you cube it, it's 8. So you get 8 from the first term. From the second term, you can write this one as 2 times square root 2. It's much better. Now you can pull 2 out. So if you pull 2 out, you're going to get 16 pi over 3. Uh, and then you're going to get 4 minus square root 2. So this is area, so I'm going to say unit square. So that's the answer. And you can see that some of the steps you can skip, but I'm writing all the details for clarification. Okay, so let's move on to the next problem. So as the next problem, we have a sequence problem. So asking what is the find the limit of the sequence. Okay, or you can also say whether the sequence converge or diverge. So that's also we can say, rather than asking what is the limit of the sequence, we can also ask check whether the sequence converge or diverge. Okay, so whether the sequence converge or diverge. That's the exact same question. uh, if we ask whether the sequence converge or diverge, we are pretty much checking whether the limit exists or not. Good. Now, how to do this problem? So you can see that, so this is the n term is given here. So you know that this is a fraction problem. When you have fraction problem, and here you notice that, so you have n which goes to infinity. In the bottom, it also goes to infinity. So it's an infinity over infinity problem. So if you have an infinity over infinity problem, so what you can do is you can use the L'Hopital's rule here. So that's one way to do this. So let's use the L'Hopital's rule. So what we're gonna do, I'm gonna say go with the limit. So it's a limit n goes to infinity a n. So which is the limit n goes to infinity n over e n plus 3n, and since this is infinity of infinity problem, I'm going to use the L'Hopital's rule here. So that means we're going to take the derivatives. So if you take the derivatives, so it is 1 over derivative of en means en plus 3, because we are taking the derivative with respect to n. Okay, we consider n as a continuous variable. Okay, now you can see it's very simple. When n goes to infinity, the bottom goes to infinity. So that means it's a 1 over infinity situation. That means this is simply 0. So the limit of the sequence is 0. In other words, the sequence converge. That's not asking here, but I'm going to say it for completeness. Say the sequence an converges. Why? There's a finite limit. That information was not asking. They're only asking what's the limit. So it's 0. Okay. So that's about that. So let's look at the next problem. So here the n term is given as n to the 2 over n. If you remember one result from this, like a calc 1, we know this result. What is the result? A limit when n goes to infinity, n over 1 over n, which is 1. That's one of the interesting information. And also I'm going to give one more information for future. So if you have any constant, if you try to take the nth root, again same thing, nth root of a constant is also 1, but here we assume that a positive, because otherwise you need complex numbers here. Okay, so those two results. And then if you remember that this is a very simple problem, so let's do in both ways. So let's say you remember this result, then the limit n goes to infinity bn, which is simply limit n goes to infinity, so it is n 2 over n. And what we're gonna do, we're gonna write this one like this. So we're gonna say limit n goes to infinity n 1 over n to the 2, but 2 is a constant. So then what we can do, we can simply bring the limit inside. So that means if you write all the math exactly correct, then this is how we, what's the next step gonna be? N goes to infinity. You can write this one as n 1 over n to the square. That's what's the next step going to be. Now we know that this limit is simply 1. So this is 1 squared, so which is 1. So that's how all the correct math works. Okay. Um, but there's another argument for this one. So what's the other argument is, you can see that you can use the L'Hopital's rule again for this problem. So let's look at how you do that argument. But this is the shortest way to do this problem. Okay, we're gonna use limit of n to 1 over n is 1. Good. So let's see the other argument. In this argument, we can use the L'Hopital's rule. So this is the reason. So what we have is we have Bn, which is equals to n 2 over n. So now, and you can see that in this case, what's going to happen when n goes to infinity? This is a 2 over n goes to 0. So we know that 2 over n goes to 0. 2 over n goes to 0. So that means what's going to happen here is it is a infinity to 0 situation. So if you have infinity to 0, which is not 0, so we don't know, this is what we normally call indeterminate form. Since this is an indeterminate form, okay, this is indeterminate form. So what we're gonna do is we can use the we try to use the L'Hopital's rule. So this is how the argument gonna work. So let's say limit n goes to infinity bn. So which is the limit n goes to infinity. So it is n 2 over n. And remember, we know this result. We have, when we have x, so x is equals to e to the ln x when x is positive. So we assume that x is positive here. So we can use this argument. So if you use this argument here, this option, so it's a limit. So n goes to infinity. So we can say e ln 2 over n. Right? So we can no, not really. So we have n 2 over n, 2n. Now we can see that the 2n is a power, so you can bring in front. So that means you can write this one as limit n goes to infinity e to the is a 2 over n ln n. Now you can see what we have is here ln n, which also goes to infinity, n goes. So it's an infinity of infinity problem. So what we normally do is when you have an infinity to 0, what we try to do is we try to convert into 0 over 0 or infinity over infinity. So in this case, since this is an infinity over infinity problem, you can take the derivatives. So we can take the derivatives and we can do this. So it's a limit n goes to infinity e. So we take the derivative. When you take the derivative, what's going to happen is so you can see that take the derivative of the, so 2 is there, and then so we're going to take the derivative of the top, so which is 2, derivative of ln is 1 over n, and derivative of the bottom is 1. Now you can see that when n goes to infinity, the top goes to 0. So that means it is simply so what's going to happen is e, so we can take the limit inside. So if you take the limit inside, so it is 2 over n situation. So that means it is e to the 0 because 2 over n goes to 0. So that means 1. So that's the other argument using the L'Hopital's rule. Okay, and then also I have seen like some students make a wrong argument. So I'm going to write this as a note. So this is the problem here. So the problem is, let's say, so we have, so they know, some of you notice that the limit n goes to infinity, 2 over n is 0, that's true. And then what they wrote is, this is a 2 and then 2 over n. Now you can see, so this goes to, some of you wrote as n to 2 over n. 2 over n is 0, so like that, so it is 1. This is not a right argument. This is not right. The reason is, you can see in this case what happened is it is a infinity to 0 situation. So you can see this is a infinity to the 0th power. So that is the indeterminate form. So you can write it like that. It's not going to work this way because n is not a fixed number. Because n is also changing. Because 0 is not actually 0. If it is 0, then that's fine. It's not 0, it's a limit. Since there are limit involved, we don't know actually what number you end up getting. So it can be any number. So this is not a valid argument because you cannot simply replace 2 over n by 0. Okay, so yeah, but you get the same answer, but it's a wrong technique. So good. The last problem on the sequences was this one. So say sine 2 pi over n, and you can see if you calculate few values. So let's calculate a few values. So what's going to happen is, so what's the sequence you're going to get? Um, so I'm going to graph the sine function. So let's graph the sine function. So it can be very clear if you do that. So like that. So what we are trying to do is we are looking at the multiples of pi over 2. See, so multiples of pi over 2. So that means you can evaluate at this number. That's the first multiple. That's pi over 2. This is second multiple, and this is a third multiple. This is a fourth multiple. So if you look at those, this is sine. So you can see, if you calculate those values, what do you get? We have sine pi over 2, which is 1. And then we have sine pi, that's the second number. Sine pi is 0. And then sine 3 pi over 2, which is -1. And then sine 2 pi, which is 0. And then you can see this pattern going to repeat now. Just going to go with the same pattern after that. So you can see 1, 0, -1, 0, like that. So that means diverge because limit doesn't exist. So limit doesn't exist. So we can say limit n goes to infinity, Cn does not exist. So that's the limit. In limit wise, that's what it says. This implies the sequence diverges. Sequence diverges. Okay, that's not asking, but that's exactly what happens. So good. So let's go to the next problem. So what is the next problem? They're asking find the sum of the following series. So it's a sum of the series problem. So if you have a sum of the series problem, you only have two options. One option is the telescoping series. Telescoping series. The other one is the geometric series. Geometric series. Those are only one you can find the sum of the series at this level. Okay, so and then you can see that what you have is here is the telescoping series. What is the telescoping series? You can write the n term as a difference of two consecutive terms. You can see the n term you can write as a difference. Okay, so that's the n terms. You can say ak in this case. That's the difference of two consecutive terms. So that's what we normally do in these situations. We're going to find the partial sum. Partial sum means you're going to add the first n terms. So that means we're going to start with, so we say a1. And then a2, a3, like that. You can add the first n terms, so the an. Good. Now let's plug in for that. So if you plug in for that, the first term, that means you're going to start the first index value, which is k equal 1. So if you plug in k equal 1, you're going to get 1/3 minus 1/4. That's the first term. The second term is you plug in k equal 2. So you're going to get 1/4 minus 1/5, like that. And then you're going to plug in the last index value, is n. If you plug in n, you're going to get 1 over n plus 2, and then minus 1 over n plus 3. So that's what you get. Now you can see there are some cancellations going on. You can see this term cancel with that, and then similarly this one cancel with the first one or the next one, and then also this one get cancelled. So that means you only end up getting 1/3 minus 1 over n plus 3. Now what we're going to do is you take the limit. So the sum is simply the limit. So we know that S infinity, that's the sum of the series, which is the limit when n goes to infinity of the sequence Sn. That's how we define the sum of the series. So that means we take the limit of this term, so which is 1/3 minus 1 over n plus 3. We need the parenthesis around because it's the whole limit. You take the limit of the whole term. Now you can see when you take the limit, this term goes to 0. So because of that, you simply end up getting 1/3 as the sum of the series. It's like a simple problem. So let's look at the next one. So next one is something like that. You may figure out that this is a geometric series, but we still need some kind of simplification. So what you notice is you just try to collect the terms which has a k, and then so that's the kind of point. So what we do, let's write it like that first. So k going from 0 to infinity. So you can write this one as 3k, and then 3 to the -1 divided by 4k to the 4 1. Now so what you can do is 3 to the -1 is 1/3. So you can write this one as sigma k going from 0 to infinity. If you bring it down 1/3 times 4, that means it's going to be 12. And if you combine all the terms with k, so these two terms have a k, so we're going to combine them. So we can write this one as 3/4 to the kth power. So that's what you get. Now you can see that is, so this is geometric now, because you can see the format of this term. So this is, you have some term times r power, right? Um, so that means this is geometric. So what we normally do is we can look at the absolute value of r. So you can see that the absolute value of r, which is so in this case r equal 2/3, 3/4, r equal 3/4. So which is 3/4, which is less than 1. That means the series so geometric series converge by the test. We know that the absolute value r less than 1 converge. So the result is less than 1 converge, greater than 1, greater than or equal to 1 diverges. So that's what we know about the geometric series. Remember, this is completely different from the P series. P series is the other way around. Yeah, good. So now what we know, so that means we know the series converge. That means we can find the sum now. Okay, so the sum. So let's write which is we normally call S infinity. So which is a over 1 minus r. That's the formula says a is the first term. So how to get the first term? You plug in the first index value. So index value is k equals 0. So if you plug in k equals 0, you get the first term, and you can see this is all 1 over 12. Okay, so you can plug in the, so just plug in the index value, first index value. So we got k equals 0. So you plug in k equals 0. So you're gonna get 1 over 12 as the first term, and then 1 minus r is 3/4. So that means 1 over 12. 1 minus 3/4 means 1/4. If you multiply the top and bottom by 3, you get 1/3 as the sum. Good. So let's go to the next problem. So the problem is asking, use the direct comparison test or the limit comparison test. So you can use one of those tests. And we know that like any problem that you can use the direct comparison test, the limit comparison test always work. Okay, so if the direct comparison test works, then you can also use, or you may also use the limit comparison test. It works that way. Okay, if the direct comparison test works, so always the limit comparison test works, but not the other way around. That means there are some problems the limit comparison test works, but it does not imply that the direct comparison test works. Okay, that doesn't happen sometimes, but not the other way around. That's something you can keep in mind. Okay, so that means we know that fact, but sometimes what happens if we try to use the direct comparison test, it's much easier compared to the limit comparison test. So for example, in this one, you notice that you are adding something to the bottom to a series which has the end term 1 over n squared. Since we have 1 over n squared, we know that that's a converging series, converging P series. So let's write the fact here. We know that, so I'm going to write this knot. So the knot is uh, the P series. P series converges um, when P greater than 1. So that means if you look at the P series, 1 over n to the P, so in this case n can start with 1 to infinity. This one converge if P greater than 1. Okay, so that's the fact. Greater than 1 converge. So you can see when you compare it with the geometric series, if the R greater than 1, that's gonna diverge. So it's the other way. Okay? Be careful with that. Okay, so that means we're gonna use that fact. So what we're gonna do is we're gonna compare this with something that's gonna converge. So if you can show that this is less than a series with terms which are smaller than yeah, if you can write this one with another series which has a term which is greater than that, so then you can see this is going to convert. So for example, we can say like this. So since 1 over n squared plus 4 is less than 1 over n squared for n greater than or equal 1, and and the sigma 1 over n squared converge and is a converging P series, with P equal to, which is greater than 1, by the direct comparison test. Sigma 1 over n squared plus 4 converges. So you can see it's a very simple argument. And then you can see that you can also use the limit comparison test, but this is much quicker, just one line. You only notice that 1 over n squared plus 4 is less than 1 over n squared, actually less than or equal, so you can have an equal sign here. Okay, but I'm gonna say a limit comparison test can be used. Okay, so you can also use limit comparison test, but you don't have to, because this is much quicker, much quicker. Good. So let's go to the next problem. So let's look at the next problem. So this is what we have. So we have n going from 1 to infinity, 2n over en. So you notice that they both has a n as a power. So that means what we can do is we can compare this with n going from 1 to infinity. Look at only the dominating terms. So that means 2 to the n over e to the n, which you can write like this: n going from 1 to infinity, 2 over e to the n. So you can see that this is geometric. This one is geometric, and you can see r equal in this case 2 over e, but we know that the e is roughly 2.7. So because of that, this is less than 1. That means the series converge. So we notice that as a geometric series converge. But the problem is, so I have a note first. So the note is, you can see, you see that 2 to the n over e to the n minus 1 is greater than or equal to, actually it should be greater than in this case because it's subtracting, greater than 2n over en. But we know that the second series converge. So because since the second series converge and the other one is larger, so you cannot use the direct comparison test for this problem. Okay, so So you cannot use the direct comparison test. Okay, so you can use a direct comparison test for this problem. So the best thing that we can do is we can try the limit comparison test, because they are asking only to use the direct or limit comparison test. Otherwise, you can use the ratio test for this problem. You can use the root test. You can use all of them. Okay, so now let's see what's the approach here. So we're gonna see an and bn terms. So I'm gonna call an and bn. So let's say this is the an, and we have bn. Okay, or we can say this is bn. This is much easier to handle. It's the same term. So let's look at the limit now. So we're gonna say limit n goes to infinity. We can say an over bn. It doesn't matter which one. So it's a limit n goes to infinity. An means 2n over en minus 1. Bn, but we're gonna make it's a division, so it's upside down. That means you can write en over 2n, and you can see that there's a nice simplification here. 2n get cancelled, and then we can look at only the dominating terms. So we're gonna say limit n goes to infinity en over en minus 1. So you may consider it's like an infinity over infinity situation and try to use the L'Hopital's rule. You don't need those heavy math here, because this is just -1, it's just a constant. So that means you only need to look at the dominating terms. So that means this limit is exactly equals to the limit, not approximation, it's exactly equal, because we are talking the limit to en over en. That means 1. So which is not equal to 0. Then but since the the series 2n over en converges is a converging geometric series, converging geometric series by the limit comparison test. The original series converges. So this is how we use the limit comparison test for this problem. And so you can see that this problem, you can also use the root test and the ratio test. Let's see how we can use them, just for your knowledge. So again, the problem is, so we have sigma n going from 1 to infinity to n over en minus 1. So this is not asking, they're asking only to use the limit comparison or the direct comparison test. But let's see what other approaches we have here. So we can use the root test. Okay, so let's say root test. That's the easiest for this problem. So for the root test, what we normally do is we're going to calculate rho, which is the limit of the absolute value of the nth root of the nth term. So let's try to take the nth root. So it's a limit. So I'm going to give you some description here. So we have so what we have here. So we have 2n. And then en minus 1 to the nth root. Remember, what we are trying to do is here is we try to look at when n goes to infinity. Since when n goes to infinity, we can ignore this term because we only need to worry about the dominating term. So that means, but if you do not have the limit, we cannot do this. So here we keep in mind. Since we are talking about the limit, that means we are only considering larger n values. This exactly equals to the limit when n goes to infinity 2n over en. So that means it's a 2 over e to the n and then nth root. So we can do that. So you can ignore the -1. So that means this simplifies. So what you get is simply you can see this is simply 2 over e, so which is less than 1. So that means the series converge. Okay, that means the series converge. So look at the argument, how we did it. So it's very simple, just like one line or two line, you're done. So also you can use the ratio test for this. Let's see how we use the ratio test. So, so if you the ratio test, so again, what we normally do is we're going to calculate an and an plus 1. So it's a limit. N goes to infinity. An plus 1 over an. So it is a limit. N goes to infinity. An plus 1. So if you consider this term is an, just plug in replace n by n plus 1. So that means since these are positive, we can ignore the absolute sign. So we have 2 to the n plus 1 over e to the n plus 1 minus 1, and then we are dividing. That means you can make it upside down. So it is en minus 1 over 2n. So that's what you get. And then what we can do again is we're gonna make the argument that n goes to infinity, so we can ignore these terms. So we don't need those terms. Or just take the derivative, but you don't need that. It's a completely valid argument. Since n goes to infinity, we can do this. So you can ignore that. And then what's gonna happen is you can see this 2n get cancelled. So so I'm gonna write the next line. So what you get is the limit. If you do not write the limit, this is not valid, okay? Because this is exactly equal. So that's the interesting part. So from the top you get 2. So you have 2, and then we have en here, and then we have en plus 1 here. Now what's gonna happen is um, en cancel with this en, only the n. So that means you again get the same thing. You get 2 over e. So which is less than 1. That means series converge. So try to make this kind of arguments. These are completely valid. This only works when n goes to infinity. Otherwise, you cannot write the equal sign. Okay, this equal sign. Good. So these are extra information how you can use the other tests as well. So you can see these are not long. It's like short. Good. The root test would be the easiest for this problem. Good. So let's try to go to the next one. So the problem says use the ratio test or the root test. You can use only the ratio test or the root test to determine for the convergence of the series. So what you notice is you can see that factorial term. So the factorial term tells you that this is a nice candidate for the ratio test. Okay? Factorial means a ratio test. So that's how we remember. Factorial means the ratio. Good. I mean, not always, but that's the kind of major situation. But there are some situations you can just use the direct comparison test and it works very well. But it's normally the ratio test. So what we're going to do, we're going to calculate the two terms. So we're going to call this is AK. So let's call this term AK. And then what we're going to do, we're going to calculate AK and AK plus 1. So what is AK plus 1? Is you're going to replace k by k plus 1, so it's a k plus 1 to the 100 over when you replace k plus, it's going to k plus 2, so k plus 2 factorial. So again, now what we're going to do, we're going to look at the limit. So let's say the limit when n goes to infinity, ak plus 1 over ak absolute value. So we don't need the absolute in this case because these terms are all positive. So let's write k plus 1 to the 100 over k plus 2 factorial. And again, it's a division, so write upside down. It's a k plus 1 factorial over k to the 100. So there is special simplification going on here. What we normally do is we're going to collect the terms with equal powers, and factorial you're going to expand. So that's the next step. So let's write it. So it's a limit n goes to infinity. So in the factorial, what you can do is, yeah, let's try the first one. So we can say you can combine these two into 1 to the 100, and then the factorial terms, so k plus 1 factorial, k plus 2 factorial, you can write it like that. So we can pull the first term out and write the rest. Rest is simply k plus 1 factorial. You only pull the first term out. Okay, that's a trick. You pull this term out. Now you can see that these two get cancelled. So that's one. And then also what happened here is you can see when k goes to, actually it's not n. We would, yeah, we made a mistake here. It should be k, not n. Yep. So this is k, this is k, and this is k. So now, so you can see when k goes to infinity, k plus 1 um, goes to k plus 1 over k goes to 1. So this goes to 1. So that means 1 to 100. So this is 1. So this limit, this limit gonna be 1. So the best way to write this one is I'm going to write the exact argument here. So it's a limit. K goes to infinity. K plus 1 over k to the 100. That's how it works. Times here we have the limit. K goes to infinity 1 over k plus 2. Now you can see that this limit is 1. So it's 1 to 100 is 1. So that means you simply get 1 times. So this one goes to infinity. Since this goes to infinity, 1 over k, so it goes 0. So it's 1 times 0. That's what you get. You get 1 times 0, which is 0, which is less than 1. So that means by the ratio test, series converge. Okay, it's actually absolutely converge. That means series converge. Let's write it like that. Series absolutely converge. Converge, this implies the series converge. Good. So this is all the argument, how the argument works. So let's look at the next one, next part. So in this problem, what you notice is that you can see the kth power here. So when you show the kth power, so we can see that, so for example, so the argument is you can see some function to a power like that. That means the root test. So that's the candidate. So we pick the root test for this. So let's do that. Again, we calculate rho, which is the limit. K goes to infinity. We're gonna take the since the variable is k, I'm gonna go with k. So it's a k absolute value, k root. That's what we do. So we can do that as a limit. K goes to infinity. So it is k plus 1 over 2k to the kth power, and then the kth root. And then you can see these two get cancelled. So you get the limit. K goes to infinity, k plus 1 over 2k, and this is simply because you can see the k and the k term. So because of that, you only need to consider those two. That means the limit is simply 1/2, which is less than 1. So by the root test, the series converges absolutely. This implies series converge. Good. You can relate to series converge. That's just extra information. Good. And you can also use the ratio test for this one, but yeah, the calculation can be little bit of lengthy. Okay, so I'm gonna write this as a note. Uh, Ratio test can also be applied, but that's not the best option, but you can still use it. It's gonna be a little lengthy. Okay, the root test can be always like a short compared to the ratio test. Okay, so let's go to the next problem. So this is an interesting problem. So it's asking to use the alternate series test. Okay, alternate series test to check whether this is converge or diverge, and also asking whether it's converge absolutely or conditionally. So, and then you can see that when you have a constant power, like see n to the 3 halves. So when you have a constant power like that, so what's going to happen is the root test and the ratio test fail. So the ratio and the root test, uh, uh, ratio and root test fail. So you can use those two tests. If you try to use that, you can see that you get rho equal 1. Okay, so why it fail? You can see that you get rho equal 1. That's the inconclusive situation. So what we're going to use is the alternate series test, especially when you have the alternating terms. So we try to use alternate series test because that's sometimes much quicker compared to other tests. So when you want to use the alternate series test, what we not do, we're going to calculate the Bn term. We're going to take the Bn term, which is 1 over n um, cube square root. So that means this is 1 over n, you can say 3 halves. So p equal 3 halves. Good. Uh, and then so because of that, and then you can see that this only in the denominator. So we can notice a few things. So what are the notice? We can notice that the limit uh, n goes to infinity. Here the index is n. So n goes to infinity. Bn, which is the limit, n goes to infinity. 1 over n 3 has this only in the denominator, so it is 0. That's the first condition satisfied. Second condition, we need to know that this decreasing, and it's obvious because n is in the denominator, so this is decreasing. So we can notice that Bn is decreasing. That's obvious. Bn is decreasing. Good. So Um, so therefore, by the alternating series test, so by the alternating series test, uh, the series -1 n plus 1 bn, right, converges. Okay, so we know that fact. Now what we want to check whether this is absolutely converge. So let's look at the absolute series. So we can look at the absolute series. So it is sigma n going from 1 to infinity. So let's look at the absolute series, -1 n plus 1 bn, the absolute one. So this is simply sigma n going from 1 to infinity bn, which is simply n going from 1 to infinity 1 over n 3 halves. And you can see here p equal 3 halves, which is greater than 1. So that means the series is gonna converge. Okay, so this is a, you can say this is a converging p series with p greater than 1. Okay, so that means the absolute series converge. So therefore, uh, this series converge absolutely. Okay, uh, so therefore, you can say therefore the original series -1 n plus 1 1 over n cube uh, converges absolutely. Converges absolutely. Good. So that's the argument. So we after we show that this uh, converges, we have this extra step here just to check whether what's going to happen to the absolute series. Okay, so the absolute series also converge. That means the original series converge absolutely. So I'm going to give you another example here, but that doesn't work that way. So let's look at that example next. So I'm going to give this as a knot. So what's going to happen? We're going to simply replace the so let's say k so let's say n going from 1 to infinity So no changes here. So -1 n plus 1. What I'm gonna do? I'm gonna replace that function by just the square root n function. So if you do that, you can see it's pretty much similar, but here only the square root, not the cube. Okay. So you can see again for this problem bn equal 1 over square root n. That means so you can see n 1/2. So in this case p equal 1/2, so which is less than 1. So what's gonna happen? So because of that, as you can see, the corresponding p series diverge. Okay, so let's see how the argument works. And you can see in this problem again, you can see limit n goes to infinity, bn, which is also very similar, so which is 0. And also see that the limit, not the limit, you can see the bn also decreasing. So bn, the sequence bn decreases. So that means by the alternating series test, the original series -1 n plus 1 bn converges. But what you notice that if you look at the absolute series, so let's look at the absolute series. If you look at the absolute series, -1 n plus 1 over bn, in this case now what we get is 1 over n 1/2. This one diverges. So diverging p series, with p equal 1/2, which is less than 1. So that means in this case the original series does not converge absolutely. Okay, so that means because absolute series does not converge, that diverge, original series converge. So you can see therefore the series n going from 1 to infinity, -1 n plus 1 square root n converges conditionally. Okay, so it's a conditional converge situation. Okay, just for your information. Okay, so let's go to the next problem. So what's the next problem? They are just asking what test you have to use. Okay, you don't want to check whether it's a diverge or converge. Just asking what is the test. Okay, what test? So how to make the argument, and what you can see is this is just an algebraic expression. So you can see it's like almost a p series with algebraic expression. Since this is algebraic, so the argument is this is algebraic. So this is algebraic. That means it is a limit comparison test. So it's algebraic. So we use the limit comparison test. So it's very simple because algebraic expression. So we're gonna go for the limit comparison test. Okay, so let's look at the next problem. If you look at the next problem, and you can see that so see we have 1 over k, so k goes to infinity. So then we know that the 1 over k goes to 0. 1 over k goes to 0, so sine goes to 0. Because we know the sine 0 is 0. And then you can see, but k goes to infinity, so it's an infinity times 0 situation. So that means this is an indeterminate situation. So what we can do, we can look at the limit. Let's see what the limit looks like. So let's say our limit k goes to infinity, k sine 1 over k. So you can write this one as limit k goes to infinity sine 1 over k over 1 over k. And you can see that these two are the same and both goes to 0. Okay, those goes to 0. So it's this is almost look like, this exactly look like sine x over x situation. We know that the limit x goes to 0 sine x over x equals 1. So that means that's exactly the same situation here because both goes to the same, because those two terms are the same. It has to be exactly the same. So that means this limit is 1. That means this is not equal 0, so we're going to use, because the series diverge, so we're going to use the test for divergence. Okay, n term test for divergence. So we're going to use use n term test, for divergence. This sometimes we just call divergence test, or sometimes we just call the divergence test. Good. Okay, so the next one. Um, so we have this one, k squared k 3 to k squared 3 to the k, and you can see that this 3 to the k term uh, tells you things like, for example, you can directly use the ratio test. Okay, so for this problem, you can use a ratio test, you can use a root test, or you can also use the comparison test. So like a limit comparison test. You can use all three tests for this problem. So let's look at one by one how it works. Only one is enough. So let's say you're going to use the ratio test. That's the obvious option. So if you use a ratio test, let's look at the limit. K goes to infinity. So we can write ak plus 1. So that means you're going to replace k by k plus 1. So k plus 1 squared plus 1 over 3k plus 1. And then here 3k over k squared plus 1. Now we know that the k goes to infinity. You only need to look at the dominating terms. So if you look at the dominating terms, what's going to happen? You can see that the we have k squared. This also have k squared. See, the dominating term is k squared. So that means they are the same. So cancel out. And then 3k get cancelled. So 3k cancel with 3k. So you only get 1/3, which is less than 1. Actually, I mean, we don't want to check, so we can say not equal to 1 because it's not inconclusive. So it's not equal to 1. That means you can test, you can use the test. So that's a ratio test. If you use a ratio test, it works. If you look at the root test, let's see how the root test works. I'm just giving all the information just for your knowledge. You only need to give one information. That's why this is long, because we are discussing other options as well. So k goes to infinity. We're going to look at the root. So let's look at the root. So it's a k squared plus 1 over 3k. The kth root. Okay, so if you have the kth root, what's going to happen is you can see, because we are talking about the limit. So when you are talking about the limit when k goes to infinity, we can make some kind of simplification here. So you can write this one as the limit. This only works when k goes to infinity. We can ignore this 1. So if you ignore this 1, you can write this one as limit k 1 over k to the square. We did a similar calculation before. And then here also 3k 1 over k. And you can see that you end up getting 1/3 again, which is not equal to 0. So that means the root test works. And you can see that you can also use the limit comparison test. That can be like little confusing, but let's see. For example, you can compare this with a smaller series which has a very similar format. So let's say, so if you try, so let sigma be k. What I'm going to do, I'm going to use instead of 3k, let's say 1 over 2k, just 2k, like that. Now if you do that, then let's see what the limit looks like. So you can see the limit of the two series when k goes to infinity. So we have k squared plus 1, 3k, and then we have 2k here, 2k over 1. So what's gonna happen here is, you can see, so if you write this one like that, so we have k squared there plus 1, no problem. But what you can bring the 2 down. If you bring 2 here as the denominator, you can write this one as 3 over 2 to the k. Now what's going to happen? 3 over 2 which is greater than 1, you can see this term is greater than 1, and this is exponential term. So exponential functions are always grow faster than any polynomial. That means the limit is simply 0, because the bottom grow much faster than the top. So that means the limit is 0. If the limit is 0, we know that the limit comparison test has like a not the like a famous version. The other version says that if the limit is 0, and then also you divide by a series which can converge. So that means that, so you divide by a series which converge, but the limit is 0, the ratio is 0. So in that case, what's going to happen is, this says that this limit 0 says that the original series grow slower than the converging series, right? Because its limit is 0. Limit 0 means the original series grow slower than a converging series. So that means it works, okay, because it's 0. If it is infinity, and if you compare with the diverging series, you can say the original series diverge. That's how we use that. Okay, good. So that's about that. So let's go to the last problem. Um, so if you look at the last problem, what it says that use any test. Okay, use any test. So you can use any test. So let's see what test we can use. For example, we know that when you have a term like that, like for example, you have a some n and a constant number like 3, something like that. We know that the root or ratio test doesn't work. Okay, so when you have log function, root test doesn't work, because and sine, cosine, those things you can use root test. So that means the root or ratio or root fails. So those two. So that means you can use a root or ratio test. And now, what if um, um, whether you can use a direct comparison? Like let's say, for example, if you try to use a direct comparison, so there's a typo here. This is not 1. This has to be 2. So let's change that. Let's change it to 2. Because with 1 it can diverge, but you have 2, so there. Good. Because ln 1 is 0, so that's why we can have 1 here. Good. Now, so the problem is why we can use the comparison test. For example, just forget about the 3, because that's just a constant. So if you try to do this one, let's say 3 over n ln n. So what's going to happen? This is less than 3 over n. So if you try to compare with 3 over n, which is a divergent series, but unfortunately it's in the opposite direction. This is not what we want. It has to be the other way around. So that means you cannot use a direct comparison. Okay, you can use a direct comparison first. So direct comparison test also does not work for this, because of it's in the other way around. So that means only option, and then direct comparison doesn't work. And then if you try to use the limit comparison test, this way you can use limit comparison test. Actually, there is a way to use a direct comparison test, but that's like a lot of thinking. You need to compare with some other function. Uh, so we are not going to go in that route. So the easiest way to look at this problem is, you can see 1 over n. 1 over n is the derivative of ln n. So you notice that 1 over n is the derivative of ln. So that's the notice. So 1 over n is the derivative of ln n. Because of that, we can use the integral test. Okay, so use the integral test. So use integral test, and that's the only test works for this one. That's the obvious test that can be used here. Okay, so to use the integral test, what we do, we can say let fx equal 3 over x ln x. Then you can see that then fx is not f, to say f. Then f is continuous, positive, and decreasing because all in the denominator, decreasing for x greater than or equal to. Okay, good. So we have the condition. Now we just check the integral. So let's look at the integral. So it is 2 to infinity. 3 is a constant. You can still write it. X ln x dx. So this is a very easy integral because 1 of x is the derivative of ln x. So you can just use the 4 formula trick if you remember. Otherwise, just use the substitution u equal ln x. So you can try that, because then the du equal 1 over x dx. Okay, so you can do that, but you can use the 4 formula trick because 1 over x is simply the derivative of ln x. So you can simply treat ln x just as x. So this is like 1 over x, just like 1 over x. So because of that, you can say, because it's an improper integral, so let's write the definition. So this is the limit. We're going to say b goes to infinity, 2 to b 3x ln x dx. But this is a very easy integral. So we do that. So it's the limit. B goes to infinity. So you can see this is simply ln, because you're going to treat this one as just as x. So it's like a 1 of x. So it's ln ln x. And then so b so to 2. So that means what we have is limit b goes to infinity. What we have is ln b minus ln 2. So ln 2 is just a number. So that means this term goes to infinity. So that means this is infinity. So integral diverges. So so by the integral test, so that means the integral diverge. So by the integral test, the corresponding series diverge. So by the integral test, the series diverges. Okay. So you may wonder why this is long, because you see that, like, we were discussing some other examples, and we also discussing why certain method does not work. So that is the reason why this is long. So otherwise, like, if you just write the solutions, you can pretty much write the complete solutions like within about 45 to 50 minutes. Okay, good. So let's try to go over, like, look at this again and again and try to understand this completely. I hope this can help you for the final exams. Thank you.